Alright, so now I will talk to you about properties and intermolecular forces, particularly in relation to how things change phase, and then looking at how intermolecular forces affect a couple of properties that are unique to liquids. So as sort of a quick review, as you guys recall, when we increase things like lattice energy, you guys have seen that melting point will go up. You've also seen that when we increase polarity between covalent molecules, melting point and boiling point also go up. So these relate to the attractions between the particles within a substance. So just a review, we know that solids maintain their shape when they are not in a container. This is because solids have really strong attractions. And these strong attractions compact the particles that are in the solid, and they really overcome the kinetic energy. The particles still do move, but they more just sort of vibrate because the solid is so dense. It's very hard for the particles to really move very far. Liquids, on the other hand, we know move a little bit more. The particles can slide around each other. But because there are still attractions, and more movement allowed, this is why liquids are able to take the shape of the container that they are in. And then when we have our gases, basically kinetic energy is so great that it totally overcomes any forces of attraction, so that the gases, they tend to move in straight lines until they hit the sides of a container or another particle. So the attractions, those forces, are less than kinetic energy. We know from before that if we heat something up, our kinetic energy will go up. If we cool something down, kinetic energy should go down. So basically, as we increase kinetic energy, we will change phase from solid to liquid, liquid to gas, or gas to liquid, liquid to solid. Okay, so kinetic energy is pretty straightforward, related to temperature. However, how do we determine some of these attractions? Well, we do know, of course, there's the attractions between ions in an ionic compound, but some of these other intermolecular forces that dictate the melting and boiling points, such as ion dipole forces, and there are dipole-dipole forces, and I'll talk about a couple others later after I talk about these two. But again, if our forces of attraction go up, then our melting points and our boiling points should also go up. The reason why is because more energy is required to overcome that force of attraction. More energy, particularly kinetic energy, required to overcome forces of attraction. Ion dipole forces, those can be seen, for instance, if you were to dissolve like salt and ionic compounds in water. Salt will ionize. Basically, it will, when it dissolves, it will split up into Na plus and Cl minus. Water, we know, is a polar covalent substance. So if you recall, polar covalent substances have those partial positive and partial negative charges. So these partial negatives can be attracted to the positive ions of sodium. The partial positive ends of water can be attracted to the negative ends of chlorine, or the negative ions of chlorine, sorry. So you have an ion from an ionic compound and a dipole, which refers to the dipole moment, which you've seen before, on a polar covalent compound. Dipole is when you have molecules of a polar covalent substance attracting to each other. So it's just, for instance, water, partial negative, partial positive, and those are going to be attracted to each other. London dispersion forces are an interesting sort of category of forces because it helps explain why certain elements can form liquids as pressure increases and volume and temperature decrease, particularly with substances like noble gases, which we assume shouldn't have any attraction for each other at all, due to all the other stuff that we've talked about, such as electronegativity. So let's take helium, a very small little noble gas. So we know that helium has 2 electrons. It fills its 1s2, so it seems to be quite happy and satisfied. However, what you have to remember is that helium is made of this 2+ nucleus, and it's got these 2 electrons floating around. Those electrons, they're not static in position like this Lewis structure might make you believe. Remember that these are in constant movement because they're in an electron cloud. So if I had 2 helium atoms coming into contact with each other and those electron clouds, well, you think of those electron clouds would be repelling each other. However, if I were to put a pause button on these 2 helium atoms, at one moment, maybe the electrons of this helium are here, and remember that electrons will repel each other, and maybe the electrons of the second helium are here. So notice how, because of the orientation of the electrons at this particular moment in time when we hit the pause button, this nucleus can be attracted to the electrons of the other atom, at least for a moment. So this is what we call a momentary dipole. Because of course, once we hit the play button and things start moving around, that will disappear. But so it's all these little momentary dipoles that allow a very slight attraction to each other. So helium can be liquefied, though of course at a very cold temperature, high pressure, so on. So we have this term for this particular property called polarizability. Which basically is the ease with which a momentary dipole can be induced. So if something has greater polarizability, so greater polarizability should mean that you will get momentary dipoles more often, and you will get greater dispersion forces. One relationship, one pattern to keep in mind is that the larger a molecule will have greater polarizability. Because they have, as we recall, more electrons, and as you know, the bigger something is, the farther away those electrons are from the nucleus. And you know, as we've seen before, that leads to a lot of different properties like lower ionization energies and so on.